I'm Daniel, and I'm going to present you joint work with my PhD advisor, Michael Pradl, who's also here, on recovering precise types from WebAssembly binaries. So I guess the first question for any research is, why would you want to care about this problem? Why is recovering types interesting or important? And for that, let's consider the simple example. On the left, you have a source program, and somebody has compiled that to a WebAssembly binary with like Clang or some off-the-shelf toolchain. And then you are tasked with understanding that binary, right? And usually that's a hard problem because, say, source code is not available and you need to do reverse engineering of malware or some third-party software, and the binary is a very, very hard to work with representation of the program. So one way, of course, would be to recover the original source code, but that's very hard in general, right? So what we focus on is recovering at least parts of the original program. And the part that we focus on is function types, in particular the parameters and return values of functions in the binary. Right? So in this example, what you would recover with our approach is this is a function that returns void, and it takes 3 parameters as input: a file handle, a pointer to a file handle, a pointer to some constant data, and a size t. And you as a reverse engineer might already infer from just those types that this is a function that writes some data to a file, right? And this is much more useful, much more easy to do given this type information than just the binary alone. So one thing I skipped over in this example, or I just mentioned in passing, is that we do this for WebAssembly binaries. So a natural question is, what is WebAssembly and why should you care? Why is it an interesting binary format to do this task form? And well, a 30-second introduction to the language. It's a low-level portable bytecode introduced a couple of years ago. You can think of it as to a first approximation like JVM bytecode, but a bit more low-level. In particular, it is statically typed, but only with 4 very primitive number types. It only has 32 and 64-bit integers and floats, right? And just from, say, an i32 argument alone, you couldn't possibly tell whether that's a pointer or an array or a file handle or something of that sort, right? So the types that you see on the right are much more expressive than the types that you see on the left that are in the binary itself. Similarly, it has WebAssembly just has untyped low-level memory, right? So there's no object graph, no garbage collection, and so on. So that, again, makes it harder to work with and recover information for you as a reverse engineer. WebAssembly programs are typically compiled from C, C++, Rust, so let's say systems-level languages, and they can be executed on a variety of platforms. Originally, the browser, so basically every browser in existence supports them natively, but also some standalone runtimes. And it's already, at least concerning its age, it's quite widely used, say, for codecs and cryptography in websites, but also for commercial applications. So there's a fully featured Adobe Photoshop running in the browser based on WebAssembly, but also some malicious applications like crypto mining and obfuscation. And especially for those cases, you might want to do reverse engineering. So that's kind of why I argue reverse engineering, and in particular type prediction for WebAssembly binaries, is an important problem. Now, of course, we are not the first to try to recover types or infer types from programs. So let's kind of map out the research space a little bit and see where we fall into this space. And I want to map it out along 2 dimensions. One dimension is kind of at which kind of programs do you apply the method to, and the other is what is the method itself. So what we do here is we recover types from binaries, not from source languages, right? So there's a lot of work on, say, type inference for Python code. We don't do that. We do it for binaries. And in terms of methods, there's kind of the classical, logical, constraint-based work, like classical type inference. And then there's the statistical machine learning-based work. And we fall into this lower right quadrant here in this matrix, right? So since there is already work on learning-based binary type prediction, the question is, what do we do different, right? Why do we need our approach? And there's a very low-level technical reason. They do it for native code. We do it for WebAssembly. But that's not a good enough reason, right? A better reason is that, or a more important reason, a fundamental reason, is that they only recover very simple types. So all of these previous binary type prediction approaches, they recover types from a fixed and small set of types, typically 7 to 30 different types. Something like, this is a pointer, or this is an int, or this is a float, but that's it, right? And this is not very instructive or not very interesting to you as a reverse engineer. And a consequence of this simple type representation that they use is that the type distribution is very imbalanced and very biased. So in particular for this Eclavier work from 2017, roughly 80% of all samples of parameter types are pointers to begin with. So if this type prediction approach gives you the information that this is a pointer, you didn't gain a lot of information, right? So it's more interesting if this type distribution is flatter and more diverse. All right, so that brings us to what we do, our contributions. First, we're the first neural type prediction approach for WebAssembly binaries. Second, we try to recover types from a more expressive type language, not this fixed small set of types. Then this makes our task, our prediction task, a sequence prediction task, not a classification task. I'll come to that in a second. And for training our neural model, we have to collect a very large data set of WebAssembly binaries with ground truth. And we make this data set and all our results and code, etc., are publicly available. Okay, so as any machine learning approach, there's two rough phases in our work, right? One is an offline training phase first, and then later a prediction or inference phase. And in the training phase, we collect a large data set, we extract some labeled data from it, and then we use it to train a neural model. I'll go over details in a second. And then you as a reverse engineer might use that model, give it a new or unknown WebAssembly binary, extract, like bash on it a little bit, such that it works for the model, and then the model gives you back a predicted type for a particular program element, so for a parameter or for a return value of a function. Okay, so let's zoom in on a couple of these pieces in this overview. And the first point I want to zoom in is the type language, because I mentioned it earlier. Our type language is inspired by Dwarf debugging information, which is a common debugging format for systems-level languages, as I mentioned before, like C, C++, Rust, Go, etc. And in particular, in our type language, we try to retain some of the expressiveness of this fully featured Dwarf debugging information. In particular, we try to recover or contain some precise information over the primitives, for example, integer sizes and signedness, which is often thrown away by prior approaches. We have a type language that supports recursion or nested types, like a pointer to something, instead of just a pointer, and that's it. We recover information such as constants about types and source level type information that really doesn't exist in the binary anymore, like structs versus classes, for example. And finally, we try to recover some names of types. So the result, okay, and kind of a more detailed comparison with prior work, which features they have and which they don't, you find in the paper if you're interested. Okay, so the result of this type language is that our distribution of types is much more diverse. So first of all, we have a lot more unique types in our dataset, more than 1,000, compared with 7 to 35. Then on the right, you see a list of the top most common types in the dataset, and you see that the distribution is a bit flatter than for these existing work, right? The topmost type is not 80% of the data distribution. Then in terms of this recursion feature or the nested types feature, a lot of types make use of that. So it's useful to have it in the type language, to not just say something is a pointer, but a pointer to a particular type. And we have a couple of those named types that I only mentioned in passing before. So you see an example of that in the lowest row of the table. Something like a size t is more instructive to you as a reverse engineer than just an unsigned int, right? And here you see the top most common types in our data. So stuff like size t, file handles, input-output streams of the C++ library, etc. Right? And those are all useful intuitions to convey to a reverse engineer. Okay, back to the overview. Another thing I want to focus on is what this model is actually doing, how it actually works, right? And for that, to be honest, there's not a big deal of innovation in the model itself that we do. So the model is just an off-the-shelf OpenNMT neural machine translation model that takes a sequence as input and produces a sequence as output. But the key point here is that we do produce a sequence as output and not a classification, right, like in the previous works. Right? So what we produce as output is a sequence of those type tokens, something like a pointer to a named type with a name file that is a struct, actually. Right? And as input, we give the model a sequence of WebAssembly instructions plus some additional information, for example, this low-level type, right? So it's already available in the binary. Why not give it the model as well as a token? Okay. Now, I mentioned to you that one kind of contribution is to have a large-scale data set, and that's necessary because if you want to train a large neural model, you need to have a large data set. And there didn't exist one for WebAssembly that included debugging information. So one thing that we did is we took all 70,000 Ubuntu packages, compiled them with debugging info, but including all the original optimizations of the packages to WebAssembly bytecode, did a bunch of deduplication and filtering to make sure that things don't leak into the test set, so we don't have inflated results. And this gives us a very large scale data set, actually larger than all of the native code data sets of the previous work. So it has more than 800 million instructions and 6.3 million type plus code labeled samples. All right, and finally, I guess that's kind of the last part to focus on in this overview. Does it actually work? What kind of types does it predict, and how do the results look like? And for that, one metric we look at, and we look at more in the paper, is exact match accuracy. So given the ground truth type from the debugging information, and the model has never seen the input binary, right? Can it predict this exact type token for token? And the answer is surprisingly yes. For parameters and return types, even for larger types, the top one prediction is right in roughly half of the cases. And if you want to look at the top 5 predictions, then it covers about 75 to 80% of the cases, right? And we also evaluated how that is influenced by the complexity of the type, so to speak. So for types that are deeper nested, a pointer to some array, how likely is the model to get this particular type right? And what you see here on the right is this for parameters and return types, that obviously if the type gets more, or when the type gets more complex, then accuracy goes a bit down, but on average, it's still the numbers that you see on the left. And one thing that we also evaluated, and kind of as a motivation for our complex type language, is, do you need this type language, or do you need a neural model at all? So kind of what's the baseline to compare to, right? And in the simplest case, you could just think of a statistical baseline where you take the low-level type as input and just produce predictions in terms of how the data distribution looks like. And for simple type languages, like in prior work, actually that gives you a surprisingly good result, but it also tells you that neural models are really not necessary for this task because the task is so easy to begin with, right? And one thing that we show here is that if you use our more complex type language, such a baseline approach wouldn't cut it. So you need to use a neural model. All right, and finally, let me show you an example, kind of to convey a bit of the intuitions about how it would work. So say this would be an input, a concrete input that actually we give to the model, right? It starts with this low-level type of the particular parameter. It then lists a couple of instructions, roughly 160 of those, and you give those to a neural machine translation model. And then the ground truth, like the actual C source code, the model obviously doesn't get it, but it's useful for us as humans to see how well it fares. And the particular parameter we are predicting here is this file handle here, the last parameter of this function. And what you see is these are the top 5 predictions of the model. And in this particular instance, at least the top most prediction is exactly the type as shown in the source code. Right? All right, and actually one more interesting tidbit is, even though the second prediction is not an exact match, at least intuitively, it's still not incorrect, right? It's just not as precise. It doesn't convey the name or the intuition that it's a file handle, but it's still a pointer to a struct, and that's not wrong. All right, and with that, let me come to kind of the high-level takeaways and the summary. So I talked about the task that we solve, which is, given a WebAssembly binary, we want to predict high-level function types for parameters and return values of functions. One core contribution and a difference to prior binary type prediction work is that we have an expressive type language that conveys a lot more intuitions to a reverse engineer than prior work. This forces us to formulate this task as a sequence-to-sequence approach and not a classification task as in prior work. And finally, for training and evaluating that model, we collect the largest WebAssembly and Dwarf debugging information dataset to date, and it's publicly available, so feel free to use it or talk to us about it. And with that, I'm happy to take questions, and of course, if you want to talk about it offline, feel free to drop us an email.
Hi, thanks for the talk. So your model is sequence-to-sequence predictions. Do you think there's any possibility of extending this from sequence to trees? So then you can have a more expressive type language with like function types, and structs could have the fields through this nesting structure. Yeah,
it's a good question. I think ideally we would like to have even graphs, right?
Yeah.
Recursive types you could conceivably predict. So we didn't try it. I cannot comment on how easy or hard it would be. Yeah, but it's an interesting idea, certainly. It's like the most immediate extension, I guess.
Cool, thanks.
Thanks for a great talk. You motivated wanting to do reverse engineering by malware or something like that. I would imagine that malware could have different properties than the data set that you trained on. So I wonder if you tried out using it on malware to see.
No, we did not, but that's a good point, actually. So the short answer is no. It's just Ubuntu packages, and usually we wouldn't consider those as malware. No, we did not, but it's a good point.
I was wondering if you could comment on what do you think would do if you went back from WebAssembly to like more ordinary binaries, x86 ARM and stuff?
Right.
Like, does this improve on the state of the art there also?
Yeah. So that's a good point. Maybe to elaborate a bit more on it, I would say a lot of the problems for native binaries are maybe partially solved already for WebAssembly, right? So if you have a native binary without debugging info or without without symbols, then just identifying functions and disassembling the binary is already a challenging problem. And with WebAssembly, because it's well specified, we get that for free. So going from the binary to the instruction sequence is basically deterministic and cannot fail, right? So that's something, if you would transfer that to native code, gets harder again. Now, kind of a more general comment, I guess, on prior work versus what we do. A lot of these papers, obviously, they are great contributions because they focus a lot on the input side, on how to represent code such that the model works. But I think there's a little bit too little focus on producing on neural models that work on how to represent code for the model. And here it's really about the output side of the model, right? And this hasn't been the focus of work before. So yeah, I guess just a general comment that a lot of work focuses on the input side, how to represent code for the model, but not so much on the output side, and that's where we focus on.
So I have a question about the dataset.
Yeah.
So as you already said, WebAssembly is supported by several compilers, more than, if I remember well, more than 40. So each compiler have a different optimization, for example, for IoT world or for blockchains or other stuff like that. So in the dataset, you are containing application of what kind of
It's a great question. So right now, this is only C and C++ applications in the Ubuntu repositories, and we compile them with Emscripten, one particular version of Emscripten, which is essentially a wrapper around or Clang, right? So LLVM-based compiler. So regarding optimizations, I would say we got that covered because we use the original optimization or the original build flags from the packages, and if they build with -02 or -03 or whatever, we don't change that, right? Now, regarding different languages, I guess a natural extension of that work would be to look, for example, at crates.io, the Rust package repository, and use, because Rust has a Rust compiler has a WebAssembly backend, and then try whether you can do that as well. In terms of not the source languages, but the types, for this particular approach, what you need is a Dwarf debugging info as the from the get-go for getting the ground truth data. And so a language that doesn't produce Dwarf debugging info, say assembly script, which compiles to WebAssembly, you couldn't use this directly our implementation. Conceptually, of course, if you do a different implementation to extract the types, that would work as well.
Thanks for the talk. I guess just building off the last question, do you think that your model could generalize well to multiple different languages, or do you see a future where you would have to have effectively a different model for each source language to try and reverse engineer?
I think that's a good question. So I cannot really hypothesize how well it would work for other languages. We haven't done the experiments. I think it's not really good science to tell something that I don't know. But I guess the general comment. Oh, can you repeat the last part of your question?
Yeah, so I guess my question is if you think there's potential future in generalizing this to handle multiple different source languages, or if you would need to, if you wanted to implement something like this.
No, actually, I just remember. I think one part of your question was, would you use different types of models for different source languages? And my comment on that is, I think that's a bit unfair in terms of the real world use case, because usually when you get a binary, finding out the source language is already part of the reverse engineering task. So if you operate under the assumption you know the precise source language, then it's kind of not a real world reverse engineering setting. So I guess ideally you would not like different models in terms of from a user's perspective for different source languages. Whether it would work better, conceivably, yes, I don't know.
Okay, cool. Thanks.
Do you analyze like a function in isolation, or do you allow information about other functions to flow between? Is there like a monolithic analysis, or?
Yeah, that's a good question. Right now, it's really functions in isolation, and so it's surprising how well it works with this very primitive code representation. So conceivably, you could track data flow across functions and then be much smarter about propagating information from, say, the call sites to the callies.
Right.
We don't do that,
Okay.
but it's a cool idea.
Thanks.